Hi everyone, we're going to talk a little bit about the universal law of gravity. Okay, so basically, universal law of gravity, or sometimes it's called Newton's law of gravity, says that everything in the universe is attracted to every other thing in the universe because gravity always is an attractive force as far as we know. So there's a force due to gravity between not only you and the Earth, but you and the moon, and you and the sun, and you and Jupiter, and you and the computer sitting in front of you or your phone. There's a force of gravity between every object in the universe. Now, we think gravity is a really strong force because it keeps us planted here on the Earth, but in reality, it's actually one of the weakest forces we know. The electromagnetic force is much, much stronger. So Coulomb's law, which we might get into later, is actually 20 orders of magnitude stronger than gravity. That's a 1 with 20 zeros behind it. So the electric force is much, much stronger than gravity, but the electric force is sometimes attractive and sometimes repulsive. Well, as far as we know, gravity is always attractive. So this is the universal law of gravity equation. Force due to gravity, in other words, weight, measured in newtons, is equal to the universal gravitational constant, which we use a capital G for, the mass of one object, the mass of the other object, and the distance between the two center of masses squared. So here's an example. Let's say we have two balls that are 0.6 meters apart from each other. Again, I'm going to give you the center of mass distance each time. And one's 3 kilograms and one's 5 kilograms. And we want to know the gravity between them, the weight that this is causing between the two objects. And so if we do the calculations, we get 2.78 times 10 to the negative 9 newtons. So it's extremely small. Immediately, these two objects, one's about 11 pounds, the other one's about 7 pounds. But they're 60 centimeters apart. But the force due to gravity is so small that on the Earth, you'll never see these two move together and touch. Now, if you get out in space and put them that far apart, eventually, over time, they will actually attract each other and touch. But in this case, that force is way too weak to overcome just a regular friction that we have here. Here's another one that we're actually going to find the distance for. So this one, I've got some much larger object, 3,000 kilogram spacecraft, and an 80,000 kilogram asteroid. But they're experiencing still a really, really small amount of force, 0.0008 newtons. And we want to just see how far apart these things have to be to get a force that low. And it turns out if you do the math here, it only ends up being about 4.5 meters. So we do the calculations, super supersymmetric to get the r squared out, then take the square root of 20, we get 4.47 meters. Another thing we can do is actually find the mass of the object. And so we've got one object, 50 kilograms. We got the force due to gravity between them, so the weight that they're experiencing because of each other, and that they're 4 meters away. Again, I'm always going to give you the center of mass distance for each one of these. And if we put it in the universal gravitational equation, we get that the mass of the other one is we get the mass of the other one to be 1.44 times 10 to the 11th kilograms. Are incredibly massive object, but they're so far apart, you really only notice the effect of gravity when we're talking about something the size of like moons and planets. And so here's a thought question. Now, our sun can't do this. It doesn't have the mass to do this, but let's say it was to suddenly collapse and become a black hole. Stay in the same location, just all the matter just got crunched down to one spot. What would happen to the orbit of the Earth? Well, yes, the Earth will get cold, but that doesn't affect the orbit. So what would actually happen? Well, here's the thing. Did the mass of the Earth change? Well, no, all the collapse happened on the sun. Did the mass of the sun change? I'm going to say no, it just all shrunk down into like one, what we call a singularity, but it didn't lose any mass. Did the distance between the center of the Earth and the center of the sun change? No, because again, we're always dealing with center of mass distances. And since none of those things changed, then the Earth's orbit would not change. The Earth would just orbit around something that we can't see. And that's actually how we find some black holes. We look for objects that we can see orbiting around things that we can't see. So one final thing that I want for this is what we call proportional reasoning. And that is, I don't give you like hard numbers to calculate. I just say we're going to change one object somehow, and how would that affect the force due to gravity or the weight between those two objects? So we first get what I call a baseline. And what that is we change all the variables to 1, and we ignore any constants. So mass 1, mass 2 is 1, distance between them is 1, and we just get rid of the universal gravitational constant. And when we do this math, we get 1 as our answer. Now this one says, what will happen to the weight if we double one of the masses? Well, you already kind of know if you double your mass, you're going to double your weight. But let's do it mathematically. So using this as an example, we ignore the universal gravitational constant, we get rid of it. The first mass we stayed 1, the second mass we went ahead and doubled, so now it's a 2. The distance between them is still 1, but it's squared. And we do the math here, we get 2. So that means the force due to gravity is going to be twice as much. In other words, you would weigh twice as much. That's a pretty easy one. Let's do this one. Let's say we triple the mass of one object and double the distance between them. Now again, I want to get my baseline. And this is something you don't really have to do after you get a feel for what that number should be. But then when we put it in our equation, again, we ignore universal gravitational constant. One mass stayed unaffected, so it stayed 1. The other mass is tripled, and the distance between them is squared. But now since we double that distance, 2 squares 4, so we end up getting 3/4. So that object, or those objects, will experience 3/4 the gravitational effect that they normally did earlier. Now, one more thing I want to talk about before I leave this, and let me go back to the equation, the very first one here. Force due to gravity. When we did that before, we did weight equals mass times gravity, where gravity is 9.8 on the Earth. Well, it turns out if we just take the universal gravitational constant, the mass of the Earth divided by the radius of the Earth squared, that comes out to be 9.8. And so if you just take the universal gravitational constant times the mass of the object divided by its radius squared, you get the acceleration due to gravity on that planet or moon or whatever it is. So that's a way that you can find the acceleration due to gravity on any planet. There's another way that we're going to use universal law of gravity combined with circular motion later on to figure out the mass of objects in space. But we'll stop there for today. Thank you, and tune again later for more video.